all three hydraulic systems was considered as high as 1,000,000,000 to 1. However, the statistical models used to come up with this figure did not account for the fact that the number 2 engine was mounted at the tail close to all the hydraulic lines, nor the possibility that an engine failure would release many fragments in many directions. Since then, more modern aircraft engine designs have focused on keeping shrapnel from penetrating the cowling or ductwork, and have increasingly utilized high-strength composite materials to achieve the required penetration resistance while keeping the weight low. Economic considerations, edit. In 2007, the cost of jet fuel, while highly variable from one airline to another, averaged 26.5% of total operating costs, making it the single largest operating expense for most airlines. Environmental considerations, edit. Jet engines are usually run on fossil fuels and are thus a source of carbon dioxide in the atmosphere. Jet engines can also run on biofuels or hydrogen, although hydrogen is usually produced from fossil fuels. About 7.2% of the oil used in 2004 was consumed by jet engines. Some scientists believe that jet engines are also a source of global dimming due to the water vapor in the exhaust causing cloud formations. Nitrogen compounds are also formed during the combustion process from reactions with atmospheric nitrogen. At low altitudes this is not thought to be especially harmful, but for supersonic aircraft that fly in the stratosphere some destruction of ozone may occur. Sulfates are also emitted if the fuel contains sulfur. Advanced designs, edit. Ramjet, edit. Main article, Ramjet. A ramjet is a form of air-breathing jet engine using the engine's forward motion to compress incoming air, without a rotary compressor. Ramjets cannot produce thrust at zero airspeed and thus cannot move an aircraft from a standstill. Ramjets require considerable forward speed to operate well, and as a class work most efficiently at speeds around Mach 3. This type of jet can operate up to speeds of Mach 6. They consist of 3 sections, an inlet to compress incoming air, a combustor to inject and combust fuel, and a nozzle to expel the hot gases and produce thrust. Ramjets require a relatively high speed to efficiently compress the incoming air, so ramjets cannot operate at a standstill and they are most efficient at supersonic speeds. A key trait of ramjet engines is that combustion is done at subsonic speeds. The supersonic incoming air is dramatically slowed through the inlet, where it is then combusted at the much slower, subsonic, speeds. The faster the incoming air is, however, the less efficient it becomes to slow it to subsonic speeds. Therefore, ramjet engines are limited to approximately Mach 5. Ramjets can be particularly useful in applications requiring a small and simple engine for high-speed use, such as missiles, while weapon designers are looking to use ramjet technology in artillery shells to give added range. It is anticipated that a 120mm mortar shell, if assisted by a ramjet, could attain a range of 22 mi, 35 kilometers. They have also been used successfully, though not efficiently, as tip jets on helicopter rotors. Pulse jets are subsonic engines which also use ram compression, but with intermittent combustion unlike the continuous combustion used in a ramjet. They are a quite distinct type of jet engine. Scramjets, edit. Main article, Scramjet. Scramjets are an evolution of ramjets that are able to operate at much higher speeds than any other kind of air-breathing engine. They share a similar structure with ramjets, being a specially shaped tube that compresses air with no moving parts through ram air compression. They consist of an inlet, a combustor, and a nozzle. The primary difference between ramjets and scramjets is that scramjets do not slow the oncoming airflow to subsonic speeds for combustion. Thus, Scramjets do not have the diffuser required by ramjets to slow the incoming airflow to subsonic speeds. They use supersonic combustion instead, and the name scramjet comes from supersonic combusting ramjet. Scramjets start working at speeds of at least Mach 4, and have a maximum useful speed of approximately Mach 17. Due to aerodynamic heating at these high speeds, cooling poses a challenge to engineers. Since scramjets use supersonic combustion, they can operate at speeds above Mach 6, where traditional ramjets are too inefficient. Another difference between ramjets and scramjets comes from how each type of engine compresses the oncoming airflow. While the inlet provides most of the compression for ramjets, the high speeds at which scramjets operate allow them to take advantage of the compression generated by shock waves, primarily oblique shocks. Very few scramjet engines have ever been built and flown. In May 2010, the Boeing X-51 set the endurance record for the longest scramjet burn at over 200 seconds. P&W J58 Mach 3 Plus afterburning turbojet, edit. Turbojet operation over the complete flight envelope from 0 to Mach 3 Plus requires features to allow the compressor to function properly at the high inlet temperatures beyond Mach 2.5 as well as at low flight speeds. The J58 compressor solution was to bleed airflow from the fourth compressor stage at speeds above about Mach 2. The bleed flow, 20% at Mach 3, was returned to the engine via 6 external tubes to cool the afterburner liner and primary nozzle as well as to provide extra air for combustion. The J58 engine was the only operational turbojet engine, being designed to operate continuously even at maximum afterburning, for Mach 3.2 cruise. An alternative solution is seen in a contemporary installation, which did not reach operational status, the Mach 3 GEYJ93/XB70. It used a variable stator compressor. Yet another solution was specified in a proposal for a Mach 3 reconnaissance Phantom. This was pre-compressor cooling, albeit available for relatively short duration. Hydrogen-fueled air-breathing jet engines, edit. Jet engines can be run on almost any fuel. Hydrogen is a highly desirable fuel, as, although the energy per mole is not unusually high, the molecule is very much lighter than other molecules. The energy per kilogram of hydrogen is twice that of more common fuels, and this gives twice the specific impulse. In addition, jet engines running on hydrogen are quite easy to build. The first ever turbojet was run on hydrogen. Also, although not duct engines, hydrogen-fueled rocket engines have seen extensive use. However, in almost every other way, hydrogen is problematic. The downside of hydrogen is its density. In gaseous form the tanks are impractical for flight, but even in the form of liquid hydrogen it has a density 1/14 that of water. It is also deeply cryogenic and requires very significant insulation that precludes it being stored in wings. The overall vehicle would end up being very large, and difficult for most airports to accommodate. Finally, pure hydrogen is not found in nature, and must be manufactured either via steam reforming or expensive electrolysis. A few experimental hydrogen-powered aircraft have flown with propellers, and jets have been proposed that may be feasible. Pre-cooled jet engines, edit. Main article, Pre-cooled jet engine. An idea originated by Robert P. Carmichael in 1955 is that hydrogen-fueled engines could theoretically have much higher performance than hydrocarbon-fueled engines if a heat exchanger were used to cool the incoming air. The low temperature allows lighter materials to be used, a higher mass flow through the engines, and permits combustors to inject more fuel without overheating the engine. This idea leads to plausible designs like reaction engine Sabre, that might permit single-stage to orbit launch vehicles, and ATREX, which could permit jet engines to be used up to hypersonic speeds and high altitudes for boosters for launch vehicles. The idea is also being researched by the EU for a concept to achieve non-stop antipodal supersonic passenger travel at Mach 5. Reaction engines are 2. Turborocket, edit. Main article, Air Turborocket. The air turborocket is a form of combined cycle jet engine. The basic layout includes a gas generator, which produces high-pressure gas, that drives a turbine forward/compressor assembly which compresses atmospheric air into a combustion chamber. This mixture is then combusted before leaving the device through a nozzle and creating thrust. There are many different types of air turborockets. The various types generally differ in how the gas generator section of the engine functions. Air turborockets are often referred to as turboramjets, turboramjet rockets, turborocket expanders, and many others. As there is no consensus on which names apply to which specific concepts, various sources may use the same name for two different concepts. Terminology, edit. This section does not cite any sources. Please help improve this section by adding citations to reliable sources. Unsourced material may be challenged and removed. July 2010. Learn how and when to remove this message. To specify the RPM, or rotor speeds, of a jet engine, abbreviations are commonly used. 1 for a turboprop engine, NP refers to the RPM of the propeller shaft. For example, a common NP would be about 2,200 RPM for a constant speed propeller. 2N1 or-ing refers to the RPM of the gas generator section. Each engine manufacturer will pick between those two abbreviations. N1 is also used for the fan speed on a turbofan, in which case N2 is the gas generator speed, 2-shaft engine. ING is mainly used for turboprop or turboshaft engines. For example, a common ING would be on the order of 30,000 RPM. 3N2 or NF refers to the speed of the power turbine section. Each engine manufacturer will pick between those two abbreviations, but N2 is mainly used for turbofan engines whereas NF is mainly used for turboprop or turboshaft engines. In many cases, even for free turbine engines, the N1 and N2 may be very similar. 4Ns refers to the speed of the reduction gearbox, RGB, output shaft for turboshaft engines. In many cases, instead of expressing rotor speeds, N1, N2, as RPM on cockpit displays, pilots are provided with the speeds expressed as a percentage of the design point speed. For example, at full power, the N1 might be 101.5% or 100%. This user interface decision has been made as a human factors consideration, since pilots are more likely to notice a problem with a 2 or 3-digit percentage, where 100% implies a nominal value, than with a 5-digit RPM. See also, edit. 1 pump jet. 2 rocket engine. 3 turboprop, a gas turbine engine used to turn propellers. 4 turboshaft, a gas turbine engine used for helicopters. References, edit.